Hi, my name is Dr. Kayla Kaiser, and this video is based on a publication by Paul D. Buckley and John A. Harrison from Massey University, New Zealand. It was published in 2000 in the Journal of Chemical Education, and it's about simulating dynamic equilibria. At equilibrium, both products and reactants are present. Chemical equilibrium is the state reached by a reaction mixture when the rates of the forward and reverse reaction have become equal. For an equilibrium to be established, two conditions must be met. First, the reaction must be reversible, and second, the rates of the forward and the reverse reaction are equal. We can write rate equations for first-order reactions. In equilibrium, we use a double arrow to represent the idea that the reaction can go both ways. To simulate a system reaching equilibrium, we can use pennies and graph paper. Initially, there are 24 pennies in heads-up state, and we call that state A, and we start out with no pennies in state B. Construct a data table like the one shown here to follow along as we allow time to pass for equilibrium to be established. Let's also record that the rate constant for the forward reaction is 0.5 or 1/2, and let's say that the rate constant for the reverse reaction is 0.25 or 1/4. At time 0, all 24 pennies are heads up, and there are 0 pennies in the tails or tails up state. In this time interval, we use the rate equation, which is the concentration of reactant A. So in this case, we have 24 pennies per volume in the space here, times the rate constant of the forward reaction, which is 0.25 or 1/2. So we see that the rate of change is 12 in this time interval. So we need to take 12 pennies and flip them to tails and move them over to the area where we're going to keep the pennies in the tail state or state B. At time 1, or 1 minute after the experiment has started, we record that 12 pennies are heads up, or state A, and 12 pennies are tails up, or state B. Then during this time interval, we use both rate equations to calculate the rate of change. The number of pennies that are heads up that flip to tails are the concentration of the pennies on the left, that's 12, times the rate constant, that's 1/2. So we see that 6 pennies need to flip from heads up to tails up. We do the same thing with the pennies on the right-hand side. Those are the tails up pennies, or the pennies in state B. We take those 12 pennies times the rate constant of the reverse reaction, that's 1/4 or 0.25, and we see that 3 pennies need to flip from tails up back to heads up and move over to state A. Now we arrive at time equals 2 minutes, and we're going to go ahead and record that 9 pennies are heads up, or state A, and that 15 pennies are heads down, or in state B. During this time interval, we take the number of pennies in state A, that's 9, times the rate constant of the forward reaction, that's 1/2. So we see that there are 4.5 pennies that need to flip from heads to tails. We see that this number is not a whole number, and since we can't flip half a penny, we're just going to simplify this demonstration by always rounding down. Looking at the number of pennies in state B, we have 15 pennies there, and the rate constant of the reverse reaction is 1/4. 1/4 times 15 is also not a whole number, that's 3.75. And again, to simplify this demonstration, we're going to always round down. So we're going to round down to 3 pennies that are going to flip from tails back to heads. Now we arrive at time interval 3. We can, in our data table, record that we have 8 pennies in the heads up state, or state A, and 16 pennies in the tails up state, or state B. During this time interval, we can calculate the rate of change from heads to tails by taking the number of pennies in the heads up state, that's 8, times the rate constant of the forward reaction, that's 1/2. So we find that 4 pennies need to flip from heads up to tails up. Now looking at state B, or the tails up state, we take the number of pennies, that's 16, times the rate constant of the reverse reaction, that's 1/4 or 0.25, and we see that results in 4 pennies needing to flip from tails back to heads. Now we will make another line in our data table for time interval 4. We're going to record that we have 8 pennies in the heads up, or state A, and 16 pennies in the tails up, or state B. For this time interval, we're going to calculate the rate of change as we have been doing. We're going to take the 8 pennies in state A times the rate constant of the forward reaction. That's 1/2, and we get 4 pennies that need to flip from heads up to tails up. Now we're going to take the 16 pennies in state B times the rate constant of the reverse reaction, that's 1/4, and we see that 4 pennies are going to flip from tails back to heads. We're going to write down that at time interval 5, we have 8 pennies in state A and 16 pennies in state B. And we can collect data for the time points 5. So we're going to do the same thing to see how many pennies need to flip from A to B or B to A, and record that for time interval 6 minutes, we have 8 pennies in state A and 16 pennies in state B. The system, we can see, has reached equilibrium because the rates of the forward and the reverse reaction have become equal. Now, in each time interval, since the system has reached equilibrium, 4 pennies will flip each way, and this means the rates have become equal. To visualize the concentration of state A and state B versus time, we can construct a graph of our data. Since time is the independent variable, plot it on the x-axis. Since concentration is the dependent variable, plot it on the y-axis. Draw points along the graph to represent the production of our product, or state B. Draw points on the graph to represent the consumption of A, state A. Connect the points with a line to emphasize when the steady state has been reached. Note that the concentrations of A and B become equal at time interval 1, but this is not the definition of equilibrium. Equilibrium is reached when the rate of change from A to B and B to A are equal, not when the concentrations are equal. And on the graph, this can be seen as the region between 3 and 6 minutes where the concentrations have become stable or steady state. A parameter useful in describing the position of equilibrium is the equilibrium constant, which we represent with a capital K. We can say that the equilibrium constant is equal to the concentration of the products over the concentration of the reactants. We could also calculate the equilibrium constant K by a ratio of the rate constants for the forward and reverse reactions. This is shown mathematically by describing the rate law for each reaction, forward and reverse. At equilibrium, the rates are equal, so we can set the rate of the forward reaction equal to the rate of the reverse reaction, and we can rearrange the equation in terms of rate constant or in terms of concentration of B and concentration of A. A summary of our data so far is shown here, with 2 ways of calculating the equilibrium constant shown in red below the graph. When the equilibrium constant is greater than 1, we say that the reaction is product favored. This is reflected in our data table shown to the right of the graph, which records that at equilibrium we had 16 pennies in the product state and only 8 pennies in the reactant state. Henri Le Chatelier said in 1888 that Every change of one of the factors of an equilibrium occasions a rearrangement of the system in such a direction that the factor in question experiences a change in a sense opposite to the original change. Let's explore this possibility by disturbing the equilibrium. What if we add more particles to A after the equilibrium has been established? In a reaction that you would do in the lab, this would mean that you're just adding more reactant to the system, and let's see how this affects our equilibrium. By adding 4 pennies to state A, now we have 12 pennies in state A, and we have the same 16 pennies in state B. As time passes, we calculate the rate of change as we did before. We take the rate constant for the forward reaction, that's 1/2 times the 12 pennies in state A, and we see that 6 pennies need to flip from heads to tails. We can do the same for our state B. The rate of the reverse reaction is 1/4 times the number of objects in state B. Currently, that's 16. So we see that 4 pennies need to flip from tails back to heads. For this time interval, now let's say we're at 7 minutes of the reaction reaching equilibrium. We have 10 pennies in state A and 18 pennies in state B. Again, using our rate constant, 1/2 times the 10 pennies in state A, we see that 5 pennies need to flip from heads to tails, and in state B we had 18 pennies there. We see that 18 times the rate constant, 1/4, gives us not a whole number, so we get 4.5 pennies, but we can only flip 1 penny at a time. We can't flip half of a penny. So following the rule to always round down, we say that 4 pennies need to flip from tails back to heads. And let's record for our last time interval that we're going to look at with this demonstration. Now we have 9 pennies in state A and 19 pennies in state B. Again, using our rate equations, for state A, we take those 9 pennies times the rate of the forward reaction, that's 1/2, and we see that means 4.5 pennies should flip from heads to tails, but we're going to round down. So that means 4 pennies. And for the reverse reaction, we have 19 pennies in state B times the rate of the reverse reaction, that's 1/4. So we have 4.75 pennies that need to flip from tails back to heads. And rounding down, as we're going to throughout this demonstration, we see that now 4 pennies will flip from tails to heads and 4 pennies will flip from heads to tails. So the system has reestablished equilibrium because the rates of the forward and the reverse reaction are again equal. The value of the equilibrium constant is still approximately 2, and the rate constants have not changed. This final slide contains common misconceptions about equilibrium. You might want to think about each of these questions in turn, and then pair up with a friend and share your thoughts. Watch this video as many times as you need to address these common misconceptions. And thanks for watching!